In this video, we're going to talk about decay series. So when a radioactive nuclide converts into a daughter nuclide, the hope is that it's forming something stable, or like that's the drive, is that the unstable nucleus is shedding something or changing its nuclear structure so that way it'll be more stable. But if it converts itself into something that is still radioactive, it'll just continue to decay until it reaches a stable isotope. And so this is what we call a decay series. It's when a radioactive nuclide produces more radioactive nuclides. And that decay reaction will just keep happening. It's kind of like it snowballs until it hits a stable state. So to determine that, if you have a nuclide that is unstable, you write out all of these nuclear decay equations. You just keep going until you hit one that is stable. There's a shortcut to kind of figure out if you know what the series is, because they can get long, especially for our larger molecules. You can just do a little bit of math instead of writing out all of the equations to figure out what your end product is. This requires knowing the order of radioactive decays, though. And so that means you really need to know your intermediates. So I find that you end up usually just doing all the work anyway, but here it is. So to determine what the stable nuclide will be, when you know the series of decays that will occur to reach it, is you count up the number of alpha and the number of beta decays that are in the decay series. And then for the mass number of your new particle, you're going to subtract 4 for every beta decay that occurs. So this is going to look like your mass number minus 4 times the number of alpha decays. And that'll be your new mass number. Then you're going to, for the atomic number, you're going to end up actually subtracting just 2 for each alpha decay. And now you're going to take into account the beta decay. Because remember, it doesn't have mass, and so it doesn't affect the mass number. You're going to add 1 for each of your beta decays. And so your new atomic number will look like the parent atomic number minus 2 times the number of alpha decays, and then plus 1 times the number of beta decays, or just plus the number of beta decays. Let's look at an example. Let's look at uranium-238. It decays through a series of reactions. And actually, there's 2 paths it decays through. After the first 7 decays, it can either go immediately to a beta or to an alpha. And so it kind of creates 2 different possible routes, but it ends up at the same place. And so here's kind of the series on the left, and then on the right, we're showing what's happening with our different decays and what our products are along the way. And this is showing the number of protons versus the number of neutrons along it. And so you're showing that our alpha decays are going to decrease our number of protons, where our let's show it. There's like an alpha decay here. And our positron decays are going to increase that atomic number, or sorry, the number of protons throughout it. And in both of these, we're going to end up at lead-206. So we can double check this. So counting these up, and I'm just going to do this example for one of these. I'm going to do it for this left-hand route. If I count these up, I'm going to have 8 alpha decays, and I'm going to have 6 beta decays. So to see if I end up at lead-206, I would take for the mass number. So for my daughter nuclide, my mass number is going to be equal to that 238 I start with my uranium, minus 4 times 8. So my mass number of 4 times the 8 alpha decays that I undergo. And that's going to give me a value of 206. Now for my atomic number, for my daughter, I am going to start with my atomic number for uranium, which is actually 92 from the periodic table. That's where I got that one. And then I'm going to subtract 2 times the number of alpha decays, which is 8. I'm going to add 1 times the number of beta decays that I have. And that's going to give me a value of 82. And so then I can use this information to say, all right, well, I've got an atomic number of 82. I have a mass number of 208. That 82, if I look on the periodic table, corresponds to lead. And sure enough, that is where both of my decay routes end up. Try this problem. It will look at the series, decay series for AM241, which is one of the elements I have a terrible time pronouncing. It's Americium, it's America EM, but yeah, I think I'll probably end up editing out like 2 minutes of me trying to say that, but I'll leave this in there. I'll go through this solution in the next video.